In this lecture, we are going to look at the HMM a little more in depth and discuss the parameters of an HMM. As you know, most machine learning models have parameters which are found using the learning process or the training process. An example of this is neural networks, where you want to find the neural network weights. Another example is the simple Gaussian, where you want to find the mean and variance. In our HMM, the Gaussian is actually part of the model, so we'll have means and variances as well. But the more important part for us is going to be to focus on the state transitions. Let's go back to our Markov model diagram. As you know, in this form, each arrow on the diagram represents a transition, and each number along the arrows is the probability of making that transition. To bring this closer to our specific example, let's consider our states. We'll be using two states, which represent low and high volatility. Note that, in general, the number of states can be considered a hyperparameter that you can optimize using the usual methods, such as cross-validation. This is because you don't actually know what the hidden states are, how many of them there are, and so on. However, this is a sort of unique scenario where we do have some idea of how many states there are and what they represent. So we can use that knowledge to constrain the degrees of freedom of our HMM. In particular, by setting the number of states to be 2. So here's something we might expect to find. If we look at a typical stock return sequence, we can see that there are generally long periods of low volatility and shorter periods of high volatility. This should remind you of our healthy and sick example. So a reasonable guess is that the probability of going from low to low is, say, 95%. And that means the probability of going from low to high is 5%. On the other hand, maybe the probability of going from high to high is 80%, and the probability of going from high to low is 20%. This makes sense because from these pictures, it's evident that we spend more time being in the low state. This is just like our healthy and sick example, where we spend more time being in the healthy state. Note that in general, these probabilities are called state transition probabilities. Without considering any specific examples, we can say that our states are represented by the indices 1 up to m. Then, we can say that the probability of going from state I to state j is p of z at time t plus 1 equals j, given z at time t equals I. Okay, so that's just for when we want to write down these probabilities mathematically. It should be clear that I and j both count from 1 up to m. Furthermore, note that these probabilities do not depend on t. That is, the transition probabilities are the same today as they were yesterday, they will be the same tomorrow, and so on. It's worth considering how many of these probabilities we will have. Well, since I has m possible values, and j also has m possible values, then it should be clear that in total, we will have m times m probabilities. Since we have m squared probabilities, and they are constant over time, it's convenient to store them in a matrix. We call this matrix the state transition matrix, and we typically denote it by the letter A. So Aij is the probability of going from state I to state j. Why is this important? It's important because this is what we will see in the code. Furthermore, let's recall that we also have the observation probabilities from each state. So for the low state, we will have one Gaussian, which is expected to have small variance. For the high state, we will have another Gaussian, which is expected to have large variance. As before, we recall that by sampling from two Gaussians with different variance, the overall effect will be that we have a fat tail distribution. And this is what we want since stock returns come from fat tail distributions. Now, one question you might have is, how do we actually find this matrix A, along with the Gaussian means and variances, given only a time series of stock returns? In this lecture, I want to give you the basic intuition for this problem, but in general, the answer is more complex. So let's start by assuming that we know which regions are high and which regions are low. That is to say, For every day in my dataset of stock returns, I've labeled them all high or low. Then, finding these probabilities is easy. All we have to do is count. For example, the probability of going from high to high is the number of times I've transitioned from high to high, divided by the total number of high days. Conversely, the probability of going from high to low is the number of times I've transitioned from high to low, divided by the number of high days. As an exercise, you might want to think about what expressions we would use to measure the probability of going from low to high and low to low. And note that, although I've said we are assuming we know which days are high and which days are low, this is not unrealistic. This is one of those scenarios where we can use domain expertise to help with our data. If we know, for example, that there was some big event that caused a lot of people to buy or sell their stocks, then we know that this was a period of high volatility. However, there is a more general way to train HMMs that do not involve having to label the data yourself. We'll discuss that more in the coming lectures. So as a bonus for this lecture, I want to give you a very intuitive idea of how we would train an HMM given a time series sequence. This is a labeled time series sequence where each day is marked high or low volatility. Note that in general, this is not the case. Okay, so suppose that this is our data set with 10 days of data. Note that each day has been labeled with an L to mean the state is low and an H to mean the state is high. So we start with 3 low days, followed by 3 high days, followed by 4 more low days. Okay, so let's remind ourselves what we need to find. We need to find the probability of transitioning from every state to every other state. That is the state transition matrix. In addition, for each of these states, we need to find the mean and variance of a Gaussian. I would recommend that you sit down and take out a piece of paper and write these out for yourself. Okay, so let's start with the probability of going from low to low. We transition from low to low 5 times, whereas we are in the low state 7 times. However, note that we will not count the final state because this actually terminates the sequence. In practice, you might have a dummy state for the start and end. So let's make the denominator 6. Therefore, P of low given low is equal to 5 over 6. We can also see that we transition from low to high 1 time, so P of high given low is equal to 1 out of 6. We can do the same thing for when we start from the high state. The number of times we transition from high to high is 2, and we are in the high state 3 times. Therefore, P of high given high is equal to 2 out of 3. Consequently, P of low given high is equal to 1 out of 3. Okay, so this gives us our state transition matrix. We have 5 out of 6, 1 out of 6, 1 out of 3, and 2 out of 3. Okay, so now let's calculate the mean and variance of the Gaussians for each state. For the low state, we have the returns 0.1 minus 0.05, 0.02, minus 0.01, minus 0.08, 0.06, and minus 0.02. For the high state, we have the returns 0.3, minus 0.5, and 0.4. What we want to do is calculate the sample mean and sample variance for each of these sets of numbers. After doing so, you should get the values that you see on this slide. Again, it's best if you try this yourself, either on paper or using a computer. Okay, so I hope that this idea of training an HMM, although it sounds complex, is actually just a matter of calculating probabilities.